Give an autonomous agent enough parallel tools, and it will eventually choke on its own output. When an agent executes multiple data scraping scripts simultaneously, the resulting data stream rapidly overflows the context window. This bottleneck creates two immediate failure states. The system either crashes into a 413 payload too large error, or it successfully processes the bloated payload and creates a spike in token costs that makes the workflow unsustainable. The Quad Code source code snapshot from March 2026 reveals a specific engineering framework designed to navigate this constraint. This architecture is a 7-layer progressive state machine. Massive data enters the top, getting intercepted and compressed across distinct tiers before reaching the core processor. Top layers use zero-cost heuristics to strip data. Only if those fail do expensive LLM-driven abstractions engage. Throughout this stack, one engineering invariant remains. Prompt cache stability is prioritized over saving token space. Robust context management requires defense in depth. Without these layers, an agent's history eventually becomes too fragmented to sustain complex multi-turn logic. Layer 1 is the tool result budget, designed to manage the specific problem of n parallel tools within a single query loop. The system enforces strict quantitative limits here. An entire message is capped at a total budget of 200,000 characters, with no individual tool permitted to exceed 50,000 characters. To enforce limits, the system routes data into 3 partitions: must reapply, frozen, and fresh. Must reapply identifies replaced results, reusing cached strings with 0 I/O. Fresh data consumes the active budget. Frozen contains older data the system intentionally refuses to modify or compress. By locking this older data, the system triggers the cache paradox. It intentionally leaves bulky text intact to guarantee a byte-level match for the prompt cache. Altering even a single character in these blocks would break the cache hit. Layer 1 proves that true efficiency requires sacrificing absolute string brevity to protect the stability of the cache. When local budgets are exceeded, the system moves to snip compact and micro compact. Both layers rely on local history manipulation without calling the API. These layers use read-write separation. The REPL view retains every block immutably. The API view sends a reduced projection to the server. To fix desynchronization from local trimming, a variable tracking freed tokens passes down the stack to update the model's estimated token count. Layer 3, microcompact, takes this further by monitoring the server's 60-minute cache time to live. When a cache naturally expires, the system executes a deep cleanup. Since the cache prefix must be rebuilt anyway, the system uses that window to strip data without incurring an additional cache miss penalty. Decoupling local state from the server's projection allows for aggressive data stripping while ensuring the user's history remains intact. At 90% context capacity, the system triggers Layer 4, context collapse. This layer applies a CQRS model to the message history. At 90% capacity, the system stops sending raw blocks and generates a distinct commit store log. Instead of raw history, it dynamically projects a compressed view to the API from this log. This projection allows the user interface to retain the full immutable history for rollbacks without suffocating the model's available context window. CQRS transforms destructive message replacement into incremental summarization, maintaining a clear path for user interaction while respecting architectural limits. If the system reaches a critical threshold of less than 13,000 tokens, it activates the auto-compact fallback. The system spawns a dedicated sub-agent tasked specifically with performing a heavy LLM-driven summarization of the existing context. This sub-agent uses a function called runForkedAgent, allowing it to reuse the main dialogue's cache prefix. Telemetry shows that without this link, the cache miss rate hits 98%, forcing massive, unnecessary token regeneration to rebuild state that was already present. Once the summary is generated, the system begins a post-compact recovery phase. The system uses a strict token budget to reload the agent's immediate state. It selectively restores 5 recently read files, active skills, and current plan definitions to seed a clean context window. Compaction must be budgeted. By reloading the exact execution state, the agent maintains its path forward even after its history has been compressed. The final failsafes are Layer 6, reactive compaction, and Layer 7, error withholding. Error withholding is a strategy of delaying the exposure of streaming errors. The system holds the error back to give the underlying recovery layers a window to resolve the issue invisibly. To prevent infinite loops during these retries, a circuit breaker caps the process at 3 consecutive failures. If the recovery layers cannot resolve the state by the 3rd strike, the system halts. The core query loop governing all 7 layers is implemented as a continuous state machine rather than a recursive function. This specific structure prevents call stack overflows, allowing an agent to maintain its state over multi-day sessions without the risk of a recursive crash. This 7-layer stack creates a stable environment for autonomous agents. Data filters through these distinct tiers to ensure only the most relevant context reaches the final execution loop. The interplay between CQRS and progressive gating prevents expensive compression layers from competing with cheaper local operations. High-performance LLM architecture requires byte-perfect cache hits and multi-layered fallbacks. These engineering patterns provide the stability needed for autonomous agents to operate effectively at scale.